Okay, today we're going to talk about energy and how energy relates to chemical reactions. So first thing we want to do is we want to define energy. Energy is the ability to do work or to generate heat. So there's two words in here that we don't know the definition of. One is work and one is heat. Well, work in physics is defined as being done when a force applied to an object moves an object. What we're primarily interested in is heat. Heat is a form of energy that moves between samples of matter because of their differing temperatures. So what is temperature? Temperature is a measure of the average kinetic energy or the energy of motion of molecules in a sample. A higher temperature means that there's greater kinetic energy or the energy of motion, therefore the molecules are moving faster. The reverse is true for lower temperatures, which means that it has lower kinetic energy, therefore the molecules are moving more slowly. There's different types of energy. Potential energy is stored energy or energy of a position or condition. We just talked a little bit about kinetic energy and its energy of motion. These two energies you've probably talked about in your physics classes. We are primarily concerned with this type of energy, which is chemical energy. It is a stored energy or potential energy where the energy is stored in the chemical bonds of molecules. We're also interested in thermal energy, energy in the form of heat. We're now going to take a look at the combustion of methane. So when we take 1 mole of methane and we burn 2 moles of oxygen with it, we produce carbon dioxide and 2 moles of water. So what does that look like on the molecular level? Well, we have 1 molecule of methane, which is CH4. We have 2 molecules of oxygen, O2. We have 1 molecule of carbon dioxide, CO2. And we have 2 molecules of H2O. What's really happening is this. The first part of the reaction is the breaking of bonds. And what's actually happening is that this methane molecule is breaking up into carbon atoms and hydrogen atoms. And these molecules of oxygen are breaking up into atoms of oxygen, which is shown here. Now this takes energy to do, which is why energy is on this side of the equation. As bonds are being broken, this requires an energy input. We call this an endothermic process because energy is going in. Endo means in, therm means heat. Okay, so what we're talking about is energy moving into the system or the process that's happening. Interestingly enough, an endothermic reaction can only proceed if energy is continuously supplied. So if the energy runs out, the reaction stops. The second part of the reaction is when we take these individual atoms here and they recombine into these other molecules of carbon dioxide and water. This is the telltale sign of a chemical reaction or a chemical change because what's actually happening are these atoms are rearranging themselves into new substances. Now, when this happens, energy is given out or released. So when we make bonds or when bonds are being made, energy has to be released. This process of making bonds is called an exothermic process, which is the exact opposite of endo. Endo means in, exo means out. Exothermic means the releasing of heat. An exothermic reaction will release energy until the reaction goes to completion. Once the reaction stops, the energy being released also stops. So taking a look at the entire reaction. On this graphic here, we have chemical potential energy. Okay, and remember the potential energy is the energy stored in the bonds. Right here, let me go ahead and get my pen out. here are my reactants, okay? And my reactants are at a certain level, and then they transition to this area here, where now we just have atoms, okay? And then those atoms rearrange themselves to now the products. Now, interestingly enough, take a look here. The reactants have more energy than do the products. So what happened? Did the energy leave or did the energy go in? Well, the answer is the energy left, okay? And we say when the energy leaves, it is an exothermic reaction, meaning that it's giving off heat in doing so. So let's take a look at how we can visualize in our heads the difference between endothermic and exothermic. What we have to visualize in our brains is a system where the reaction is happening and the surroundings, which is the area that surrounds the system or the reaction, what we call the atmosphere. In an endothermic reaction, get my pen out again, heat is going in. Therefore, we say it's endothermic. Heat is going into the system. We also can denote that another term, which is called the delta H, or the change in heat, is going to be greater than 0, or a positive number. So if you see a delta H that it's a positive number, that means that it's endothermic. What's really happening is when heat goes in, that means that the surroundings get colder than the system. And the system is gaining energy or heat, and therefore it's raising its temperature as this heat is moving. The opposite holds true in an exothermic reaction. Again, what's happening is heat is leaving the system or the reaction and going to the surroundings. So if that's true, then the heat is leaving the system and going to the surroundings. So therefore the surroundings are gaining a higher temperature or becoming hotter than the system itself. And the system's actually losing heat. Examples of endo and exothermic processes are this. So again, you have to think of system versus surroundings. So if we said melting of ice, is that an endo or an exothermic process? Well, if you think about melting of ice, you need to think about what's happening. Well, in order to melt ice, heat has to be going into the ice in order to melt it. Therefore, it's endothermic, or a positive delta H. How about freezing of water? Well, in order to freeze water, we have to remove energy from it, or remove heat. And if we remove heat, that means it's exothermic, or a delta H that is less than 0, or negative. Last one is real easy, the burning of wood. When you burn wood, you're actually releasing heat to the surroundings, and therefore it's an exothermic reaction, or when the delta H is negative. Last thing I want to mention is the law of conservation of matter. Okay? And that means that energy is neither created nor destroyed in any mechanical, physical, or chemical process, but changes from one form to the next. Actually, this shouldn't say matter. This should say energy. So we're going to go ahead and write that here. We're going to cross this out, and we're going to put energy. We're just going to put energy here. The law of conservation of matter still holds true with any type of chemical reaction, but what really is happening as well is the law of conservation of energy, which states that energy is neither created nor destroyed in any mechanical, physical, or chemical process. So what's actually happening, since it's not created nor destroyed, it's just changing from one form to the next. Here's an example of that. When we take a look at this physical process here, we are actually taking a look at potential and kinetic energy. These guys are at a certain height, therefore they have a certain potential energy, and as they fall, that falling causes them to change potential energy to now kinetic energy. In order to move these bikes, we're actually taking chemical energy stored in our food and transforming it into kinetic energy or mechanical energy, okay, where we can actually take the energy from our food and use it to pedal our bikes. Okay, so that's a law of conservation of energy. This holds true in chemical reactions as well. Here's an example: the synthesis and decomposition of water. It releases or consumes the same amount of energy no matter which direction you go. So here's the synthesis of water. Synthesis means combine. So we take H2 gas and O2 gas and we combine it to make 2H2O. And what that does is it actually releases 12.04 kilojoules of energy. Now when you see an energy term on this side of the equation, that means it's being released. So therefore it's an exothermic reaction. And therefore your delta H is going to be, your delta H is going to be negative. Okay? Here's the decomposition of water. And again, as you notice here, it is the same number. Okay? It doesn't matter if we're going in the forward direction or the reverse direction, it's still going to input or output the same amount of energy. In this case, you see that the energy is a reactant. Therefore, it means that energy is being inputted. So therefore, our delta H term is going to be positive. You guessed it. Okay? So again, I just want to make it clear that it doesn't matter which direction you're going, the same reaction in the reverse or the forward direction will still have the same energy, the absolute value of the same energy term. It just determines whether or not it's positive or negative, or exo versus endothermic. Okay, that's the end of this lesson. If you have any questions, please go ahead and ask during class. Thank you.